So related to the idea of a vector space is the idea of a subspace. A set W that's a subset of a vector space V is called a subspace of that vector space V if a simple condition is met, and that is that set, if you were to attach to it the same operations as this larger vector space V, if with those same operations, if it itself were a vector space, then we call it a subspace. So no surprise with the language. It's a subset that is a vector space, and we combine to get subspace. Okay, so here's an example. Let's consider the collection of ordered triples. So collection of points in R3 for which the third coordinate is 0. So this is what you might think of as the xy plane in R3. And the assertion here is that this is a subspace of R3. So it's clearly a subset of R3, and all these points are in R3. Now you have to confirm that this is a vector space, specifically using the same operations as R3, namely using the usual vector addition, using the usual scalar vector multiplication. Check that this is a vector space. Okay, now certainly one thing that we're going to need in order for a subset to be a subspace is we need for the operations on V to actually be operations on W. In particular, one thing we're going to need is that if we take two vectors in this W thing, we need to be able to talk about their sum. Well, of course we do. We need to have an operation of addition, but an operation of addition, if W is going to be a vector space, that sum has to also be in that would be vector space, so it has to be in W. This is what went wrong in an example that we saw in our discussion of vector spaces. We saw that this plane, using the usual addition, had this problem that this vector satisfies that equation and therefore is in W. This vector satisfies that equation and therefore is in W. But when you add them, doesn't satisfy that condition anymore, right? So what we have here is a situation where, using the usual addition, we could take two vectors that are in this set W, and the sum is not in W. So this would be a problem, as it was in this example. Okay, so the observation then is that this is a requirement. If W is going to be a vector, if W is going to be a subspace of the vector space V, then certainly we need that any time that you have two vectors and you add them, that has to stay in W. So the terminology we used, that we use here, is that the set W must be closed under addition. And very loosely speaking, you can think of the motivation for this term closed is that if you take things that are in W, addition requires that you stay in W. So you can't get out in some sense. Very loose sense. Okay. Similarly with scalar vector multiplication. If you have a vector in W, well, we need to have a scalar vector multiplication, and so this scalar vector multiplication that hopefully is an operation on W, well, that product had better also be in W. And analogously, we say that a set that has this property is closed under scalar multiplication. Okay. Now, of course, go back up here to our example, and certainly we need those two things to be the case in order for our operations to in fact even be operations. But we also need for the set to be a vector space, and there's a list of 8 requirements then that have to be checked, or one would think. The amazing thing is that if you have a set, a subset of V, and if it is closed under addition, and if it is closed under scalar multiplication using the operations of V, that's enough. Amazingly. So here's the statement of the result. You have a subset of V. It's got to be non-empty. This is a formality issue, but if it's empty, it can't contain the 0 vector. Anyway, it's a little silly business. But if you have a subset of V, and if it is closed under addition and closed under scalar multiplication, that's all you need to check. It is definitely a subspace of V, and you don't have to check those 8 properties. This is a theorem. Now, the proof of this theorem is actually pretty straightforward. The proof is the observation, mostly, that the conditions that one would think you'd have to check, those 8 conditions, those are conditions on the operations. Those are conditions on, for example, how plus works. So you need to be sure, requirement number 1, was that V plus W has to always equal to W plus V. Well, how do I know this is true? Well, because I already knew it was true. And by assumption, we're using operations from the existing known vector space capital V, for which our plus is the addition operation. So because it's the operation for V, we know that this requirement on the addition operation must be satisfied. Likewise, most of the other requirements, most of those other 8 requirements are requirements on the operations, and we already know they're satisfied because they come from an existing vector space. So really it's just an observation that the observations we felt like we probably needed to check have already been checked. And there's only 2 exceptions. The 2 exceptions are properties 3 and 4. Property 3, we need to show that there is an additive identity. We need to show that the 0 vector in particular must be in W, and this is an immediate consequence of W being closed under scalar multiplication. So if you take any vector in W, any vector at all, we know by being closed under scalar multiplication that if you multiply by any scalar, so for example 0, that the result must also be in W. And, well, because anything times the scalar 0 must be the 0 vector, we conclude that the 0 vector is in W, as property 3 requires. Likewise, for additive inverses, for any vector in W, take that vector, multiply by the scalar -1, and it's mentioned in the last chapter, the last section, that that gives the additive inverse for W. Well, if this W is known to be in this set W, then multiplying it by a scalar gets you something that is therefore known to be in W, because W is closed under scalar multiplication, and therefore the additive inverse is also in W.